Okay, so we've just, changed our program so we can calculate a molecular potential by solving Schrodinger's equation for a molecule at different bond lengths. And now we're going to calculate vibrational frequencies of this molecule for this potential that we just scanned for. Zooming out one step further. And so I'm going to once again add another page to our tab here, and I'll call it molecular potential. And here we will solve vibrational frequencies of the potential we've scanned for. So I'll make another case in my case structure on my block diagram. And what we want to do is read the values from this plot, essentially, and use that as the potential. So I'm going to create a property node with the values, so I can read the values that are currently displayed on there. I'm going to rename this too, so we don't just have XY graph 3 there the whole time. And then I'm going to unbundle our X and Y values. The X values will actually go straight through here. In every other iteration of our program here, we've taken the X values that we've made in our make X. But now note that we're not using them anymore. We're not using those X values. We're using all the bond lengths that we scanned through, which were our X maxes. So we're going to take this from a new spot here. Also, we can go ahead and connect that to our transition probability calculation, because this is a one-dimensional system again, so we want to use a transition dipole moment related to our dimension. And the Y values, we want to make our potential. We've got some more things here. We've got a mass. What will the mass be? Well, we're solving for vibrational frequencies, and so we're going to need the reduced mass of the bond. So we'll do mass 1 and mass 2 of our two atoms in the bond. These are in atomic mass units, grams per mole. And for hydrogen, yeah, something like 1.007 for H2, that is. And on the block diagram, we need to calculate a reduced mass, which is the mass 1 times mass 2, divided by mass 1 plus mass 2. There's our mass for our kinetic energy. You use the reduced mass when you have relative motion of two bodies and you're calculating the kinetic energy of that. Now we need to figure out the dx, the spacing between the x values. Can't get it from make x anymore. It instead comes from our step way up here. We could wire this directly in, but just to keep it a little more localized here, I'm going to just read with index array the first two elements here of our x value array, index 1 and 0. Oops. And then just subtract them, because that will also give us the difference, and that way if I end up changing this later, program will correct itself. Cool. I think that'll work. All right, there we go. So let's zoom in. You see we are displaying our potential here. Negative 100,000 should be a good range. I'll zoom in a bit on the x-axis as well. Okay, so there's our V equals 0 energy level. You can tell it's the V equals 0 because it's the modified version of the 1/2 period of a sine function for the guitar string wave functions we've been talking about for a while. The energy is right here. It's on a scale still where 0 is the where the ionization energy of hydrogen is. So this number by itself doesn't make a lot of sense. When you see a potential energy curve plotted in most situations, either the asymptote will be 0 or the bottom will be 0, but it doesn't matter. Let's save this wave function and find our V equals 1. A little bit too far. There we go. Okay, there's a transition wavelength. That is something in the near IR. Vibrational frequencies aren't, generally, nanometers isn't even a function of frequency, but let's say vibrational transitions aren't typically plotted in nanometers. They're typically plotted in inverse centimeters. So I'm just going to make a another indicator here before we convert to nanometers for just the transition energy in inverse centimeters. Okay, run it again. So 3,200 inverse centimeters. That's actually, pretty close to the vibrational frequency of a molecule like this. H2, I believe the vibrational frequency is more like 3,800 or 4,000 or something like that. Remember, we solved it in one dimension, and this is also H2 plus and not H2. But this is a reasonable vibrational frequency. So that was gotten by taking the energy difference between the V equals 0 and V equals 1 state. That is just equal. That transition energy is also equal to the vibrational frequency. And because the frequency of that light is resonant with the frequency of the motion of the vibration. So if you convert that inverse centimeters into inverse seconds, then you would get a Hertz value, which is how many times the molecule, the bond vibrates per second. Another thing we can look at here is the transition probability. This is a non-zero value. But if we go up to the to simulated transition between the V equals 0 and the V equals 2, the transition probability decreases by another factor of 100. And if we go further, it gets smaller still. So for a harmonic oscillator, the selection rule is a hard delta V must change by plus or minus 1. However, for a real molecule, since this potential is not actually symmetric, that selection rule is relaxed, and you do get non-zero transition probabilities for delta V's larger than 1. And these would be called vibrational overtones in your spectrum, and they're usually about 100 times weaker than the fundamental, and indeed that's what we see. But they are still experimentally visible, and so this is reproducing what we observe experimentally quite well.